Are you feeling curious?
Show of hands, show of hands.
Today on Curious Crew,
Oh, I can feel that too.
temperatures rise
That steam's coming off.
as we explore the science of
This is like the best experiment I've ever done.
thermal conduction.
This is a hot topic.
Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. By the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources. More information is available at consumersenergy.com/foundation. Consumers Energy Foundation, supporting education and building sustainable communities in Michigan's hometowns. And by viewers like you. Thank you.
Hi, I'm Rob Stevenson, and this is
Curious Crew!
Welcome to the show, everybody. We always like to start every episode with a couple of discrepant events because discrepant events stimulate.
Curiosity!
That's exactly right, and I have some perplexing ones for you today. And in fact, I'm going to start with something that looks pretty obvious. This is a little souffle cup. Patrice, I'm going to give you this souffle cup. You're welcome. Patrice, can you tell me what material that is made of?
Paper?
It is paper. Now, Patrice, what would happen if I put that paper souffle cup in a flame?
It should burn.
That is exactly right. Now, this is a very interesting discrepant event, and not one I'd really want you to try without an adult present, to be sure. We're gonna take proper precautions here, safety first. I have taken one of these souffle cups and filled it about half full of water, and we're just going to light this burner directly underneath the paper cup, which seems like a foolish thing to do, doesn't it? Okay, I'm gonna let that sit for just a minute, and Carmela, you're gonna help me with the next discrepant event. We have two blocks that are right in front of you. I'd like you to handle both of those black blocks and tell me what you observe.
The block on the right is a lot colder.
Okay, I now am going to place a couple of O-rings on top of each, and we're gonna take an ice cube, wow, these are cold, and I'm gonna place them one on each block, and we're going to sort of notice what's going on there. Carmela, what are you noticing?
This one that I thought was colder is melting a lot faster now.
Which seems a little perplexing. Speaking of perplexing, I wanna come back over here to my paper cup. I'm gonna extinguish this flame for a moment. Although what's fascinating to me is if you've ever boiled water, you have seen how there's little bubbles that sort of percolate from the bottom. But take a look at this paper cup. Is it charred at all?
No.
Not at all. And you can take off your goggles, my friends. We've got some interesting discrepant events here. Look at that ice cube. Oh my goodness. I'm gonna have a drippy mess in just a moment. Now, I'd like to invite three of you to take part in a little scientific modeling to see if you can explain these phenomena by the end of the show. You can use evidence throughout the show to revise your thinking, but who would like to do a modeling moment today? Who'd like to try that? Okay, Ben, Mackenzie, Genesis, you three are gonna do that. Now, does anyone have a prediction on what we're gonna be investigating today? What do you think? Caleb, what do you think?
Thermal energy, maybe?
Ah, thermal energy, excellent, and more specifically, thermal conduction. Stick around. This episode is hot off the press.
So let's figure this out. Ben, what did you notice?
It was really surprising that cup of water did not ignite. That flame was really hot.
I know. It even seemed like the water began to boil.
And I've never seen an ice cube react like that. It's almost as if it was on a hot plate.
Yeah, it was really weird. Carmela said that the first one to melt the ice cube was the colder one. That seems kind of backwards to me.
When objects touch each other, the energy from the particles will transfer from the warmer object to the cooler object. This is because the particles in the warmer object vibrate faster, and when they bump into the slower moving particles in the cooler object, the energy is passed along. You may have noticed this when you pick up a warm mug and it begins to warm your hands, or when you make a snowball and your hands quickly get cold. Whoa, that's cold. Hot chocolate, here I come.
So I know those discrepant events were a little perplexing. And now it's time to try to make sense of what we mean by thermal conduction, okay? To start, Max, you're gonna help me out. Over here, I've got this cup, and inside the cup, I have a plastic spoon, a metal spoon, and a little wooden popsicle stick. And on the very top, I've got some butter squished on the top. And what we're gonna do is I'm gonna put some hot water inside the glass. And I'm curious to have you predict, which one do you think the butter is gonna start to melt and slide down first?
I think it's going to be the popsicle stick because the wood might burn off of it.
Let's pour this in and take a look and see what happens. I'll just do it about 3/4 full. And the first thing that we have to think about with thermal conduction is now we have particles that are touching each other. We've got the hot water touching the handles of the spoons and the base of the stick. And some of those particles are gonna start bumping into each other. In fact, the ones that are really hot are bumping pretty quickly, okay? We're gonna illustrate this another way. We'll keep an eye on that. Ishi, you're gonna help me over here.
All right.
In this cup, we've got 4 items. You're gonna notice there's a glass test tube. I have an aluminum strip, another popsicle stick, and a piece of plastic. I'm gonna put some water in here, and what I'd like you to do is to report to us, when do you feel a temperature change on any of these items? And you can start touching them now at any time you want. And you might even want to use both hands so you can start checking different things and see what's going on.
Well, this aluminum strip is starting to get a little bit hotter than I think it was when it was starting.
Okay, so a little hotter.
Yeah, and
Oh, I can feel that too. I can definitely feel that.
and the plastic still feels like room temperature.
Okay.
And the test tube still feels like a little cold.
Okay, interesting. So we're really only noticing the difference on the aluminum strip, and you can feel a difference there. Let's think about what's going on for just a moment. We're gonna keep an eye on those spoons as well. Now, you felt it the fastest in the metal spoon.
Yeah.
Now, I mentioned to you that when two things are touching, thinking about taking your hot hand and put it against a cold hand and like, oh, the cold hand person goes, oh, that feels so good. Because now we have that energy going from one person to the next. Think about it this way. If we can have a faster moving particle bumping into others, we can pass that energy along right through contact. And that's the idea of thermal conduction. Now, believe it or not, if we wait long enough, this spoon is going to start to get hotter than the plastic or the wood, and we're going to start to see this butter slide down. So tell me what's in common with these two, Genesis.
The metal is getting warmer quickest, so I think the contact between the water and the metal is causing an energy transfer, and metal just happens to be the one getting warmer quickest.
Excellent, better energy transfer. So then you have to say to yourself, why is it? What is it about metals? Well, here's something that's really interesting. There are electrons in metals that are called free electrons, and they are free to escape and collide into other things really, really fast. And so if you want a good thermal conductor, you can think about metal. Thermal conduction, it's pretty energizing.
Atoms in solids are much closer together than the atoms in liquids and gases, so conduction happens much more rapidly. Particles easily bump into one another, and if there is a big temperature difference between the objects touching, the rate of energy transfer is also higher. But not all solids conduct thermal energy equally. We saw how the metal was warm to the touch and began to melt the butter on the spoon. The wood, plastic, and glass transferred the energy much more slowly.
So as we explore more with thermal conduction, I want to share this little thing. And Finney, I'm going to hand this to you and describe for me what we have there.
So on this end, it looks like a piece of wood, and on this end, maybe like a copper pipe, and in the center, there's a piece of burned paper.
That's a very, very good observation. And you're correct. I took a wooden dowel and I forced it into a copper tube, and then I took an ordinary piece of paper and wrapped it really tight around the whole thing, used double-sided tape to hold it together, and you can tell that one part is burned. My question for you, Caleb, is can you tell where the two ends meet?
Maybe like at the end of the burn mark, just like in the center of the paper.
Okay, so like
that
right
maybe?
there. You're absolutely correct. And the way I know is because of the experiment that I did. I ended up lighting this burner, I held it on this wooden end, and believe it or not, I put the paper inside the flame and I kept rotating it around. Now you're noticing only one side is burned though.
Yeah.
Okay, let's think about this. The paper is touching metal. The paper is touching wood. What's happening to the energy here on this side? What do you think, Finney?
I think that the energy on the metal side is being conducted away from the paper.
In fact, it's conducting so fast, it's preventing this from catching on fire. Not so on the other side. When I was doing this, I was holding the wooden side. Why wouldn't I want to touch this side?
Because the metal's hot.
That's exactly right. Now, we know metal is a really good thermal conductor, and here we can actually see it, so much so that it prevents the paper from actually igniting, which is really kind of unusual. Now, I've got another scenario over here. I've put together a fork and a spoon and pressed them together. And you'll notice that right here, I've put a match going through the tines of the fork. Now, Patrice, what's gonna happen if I light that match?
The fork and the spoon will fall.
That is a logical prediction. Safety first, my friends. Let's get some goggles on here. And I am gonna light this, and I'll encourage you to watch it closely because it's pretty fascinating. And as we watch this, we need to think about what's happening with thermal conduction. Notice and watch closely. The flame went out. You can take your goggles off. Did you notice where the flame went off there, Caleb?
Like right at the edge of the glass cup.
Exactly, right where it's touching the glass. I can even knock off this little piece, which makes it look even more interesting, and it still hasn't fallen yet. So we're thinking, okay, not only is that really cool for balance and center of mass, but it's also a great example of how energy is going to transfer into the glass, so much so that the wood stops burning. Amazing. So we've seen that not all solids conduct thermal energy equally. In fact, some just can't take the heat.
Stepping out of bed onto a hard floor feels really different than stepping onto a carpet. Even though the temperatures might be the same, the hard floor feels colder because it conducts your body heat away much faster than the carpet. Try touching a metal faucet and compare the temperature to the surface of the table. The faucet will feel colder for the same reason. It is a great thermal conductor, transferring your body heat away so it feels cold. Thermal conduction really is cool.
We've been having fun with collisions, but I have a great STEM challenge for you.
Building and testing the bumper cars was a really fun experiment.
So we got our bumper car track ready. Let it go. Whoa!
It was really shocking to see how far some of the cars went.
Ooh, another great elastic collision.
You really wouldn't expect something to be able to do that.
That was crazy elastic.
STEM challenge.
So have you been having fun investigating thermal conduction today? Yeah! I'm so glad. Now, how many of you have ever made oobleck before? Show of hands, show of hands. Okay, so a number of you have. Now, this is going to be an interesting recipe for oobleck. This is thermal oobleck. You'll see what I mean. Are you ready to start making your recipes? Yeah! Go for it.
I think we should start with the cornstarch and then start adding in the water.
So what if it's like this? It colors it, but also changes the texture.
Dr. Rob has us making thermal oobleck.
Just pour it all over.
It's kind of like slime in a way.
Oh, it feels so weird.
We're mixing together cornstarch, water, and thermochromic pigment.
This feels so good.
When we mix them together, it starts to sort of solidify a little bit.
The most challenging part about the oobleck was getting the right consistency that you wanted.
It's watery.
You should always have cornstarch and water next to you, so if you need to add either of them to your experiment, you can.
This is way too much cornstarch. Oh, it's turning pink.
At first it was like pink with the heat from our hands, and then it started turning like gray, and it wouldn't go back to pink anymore.
Once it leaves my hand and it starts cooling down through the air, it becomes gray.
If you're doing this at home, I would definitely recommend to get a large area to do this over, even if it's just to have some newspaper under your work area to keep yourself clean.
I'm gonna have to wash my hands like 7 times.
This is like the best experiment I've ever done.
Okay, I'm gonna interrupt you. Oh my, what a mess, but what fun. So I can tell you're enjoying the thermal oobleck, but I'm curious, what are you noticing? I'd like to hear some observations. Max, tell me an observation that you've noticed.
I noticed that when you squeeze it, it becomes really hard and it kind of cracks a little bit. But then you just let it sit in your hand for 1 second and it becomes almost like a liquid.
Excellent. That's a non-Newtonian fluid, which is really strange. Characteristics of both solids and liquids. Actually, I'm going to jump over to Patrice. Patrice, tell me something that you noticed.
I noticed that the longer you play with it, the grayer it gets.
Oh, that's interesting. Okay, and Genesis, what is something that you noticed?
I noticed that as we were playing with it and it was in our hand, it became a really nice shade of pink because it was getting warmer. And then as it dripped, it started to become gray.
Interesting. So this thermochromic powder that we've added changes color from your heat, right? It started as what color, everybody?
Black.
Black, absolutely. And then you started to play with it and it started turning pink. Now we have different thermochromic powder that we can use with different color changes. However, some require a lot more temperature to be able to change. This is perfect to change from your hands. Thermochromic powders, a pretty fun way to make an oobleck recipe that much more enjoyable.
The crew had a lot of fun investigating thermochromic pigment, but engineers have thought of other clever ways to use that technology. One example is a strip that can be placed across someone's forehead, and if they have a fever, the strip will change color. You can also find baby bath thermometers that will change color to the ideal water temperature to make sure the baby doesn't get too cold or get burned. Those are great designs.
So we know metals are really good thermal conductors, right? This little device is called a conductometer or a conductometer. And you'll notice there are 5 little arms, and each one is a different kind of metal. So we've got aluminum, we've got brass, we've got copper, we've got stainless steel over there, and then iron up front. And you're gonna notice on the ends of each of these little rods, I have a teeny tiny little bit of butter. Now we're gonna light this candle underneath here. And what might happen, Mackenzie?
The heat will transfer around the rod and make the butter fall off.
Okay, now I've got 5 different kinds of metals. Which one do you think the butter's gonna fall off of first?
Aluminum.
Okay, excellent. We're gonna come back to this in just a minute. And Ben, you're gonna help me out on this one, because this was an investigation that Benjamin Franklin did a long time ago. So Ben, Mr. Franklin, I thought you would be perfect for this. Notice here, we've got 2 metal strips. One of them is copper and one of them is iron, and I've got them strapped together with a rubber band. Now, Benjamin Franklin did not use rubber band, but he did have 2 pieces of metal strapped together, and then he dipped them into oil. We're gonna use water. I'm gonna pass this over to you. Describe for me how they feel.
Well, this one's a bit colder than this one.
Okay, so it feels a bit colder. We're gonna pour some hot water in there. And what I'm gonna ask you to do, yeah, you can see it's hot. That steam's coming off. Go ahead and put the base of it in. So can you feel a difference in one of them?
Yes,
Which one?
the copper.
The copper. It's getting warmer, isn't it?
Yeah.
Now, the amazing thing is, yeah, that is getting warm. Amazing. Now, this is 2 different sizes pieces of metal. If I use the same length and the same diameter, the copper, the thermal energy will travel 10 times faster. That is really fast. And you might be thinking, how can there be such a difference? And that's because of the bonds of the molecules that are in there. They've got these free electrons and they can escape really, really fast out of copper. So if that's true, Carmela, I've got a wondering for you. Which one might we see the butter fall off of faster, copper or iron?
Copper.
Exactly. That would make a lot of sense. And in fact, if we look at that copper right now, it is starting to liquefy as we speak, which means it is going to drip off. And notice over here, your prediction of aluminum is also starting to liquefy and it's going to drip off. But take a look at these 2, iron and stainless steel. Not much happening there. In fact, The stainless steel, it'll take about 13 minutes before that's going to fall off. That's amazing. So when we think about copper in particular, look at the bottom of your pots and pans at home. It is very likely it is made of copper because it's such a good thermal conductor. Pretty amazing. Hey, see you later.
Metals are better heat conductors than many objects, and this is because they have free electrons that collide and transfer energy from one atom to the next. Thermal energy conducts differently in metals, depending on how strong the bonds are between the particles. Metals with weaker bonds, like aluminum and copper, are excellent thermal conductors. That is why an aluminum pot will heat up so fast on a backpack stove. That was quick.
So, we know that metal is a good thermal conductor.
That's true. Ishii felt the heat rising through the metal strip way quicker than all the other ones.
We also saw the butter melt faster on the metal spoon. One of those blocks must be metal in order to transfer heat so fast.
I noticed the half-charred paper didn't burn when it was against the pipe, and maybe the water was doing something similar with the paper cup.
I see what you mean. Maybe they are both transferring energy away from the paper.
So have you had fun investigating thermal conduction today, everybody?
Yeah!
I'm so glad. I know you were keeping your cool, too, while you were talking about these discrepant events. But what have you figured out about the paper pot, Mackenzie?
The paper never burned because the water is in the paper cup, so the energy from the flame kept transferring to the water.
The paper didn't reach the flash point to ignite.
That's exactly right. The temperature for the flash point of the paper is actually higher than the boiling temperature of the water. Now, what that means is we can get the water boiling and the paper will stay intact, which seems really strange under that direct heat. That works fine until all the water evaporates out. Then we've got a problem, because then once the paper is empty, it would ignite. This is definitely one to let an adult do, or better yet, just watch it on Curious Crew. But what have we figured out about our ice blocks, Ben?
The colder one melted the ice cube faster. We think it has something to do with the different materials.
Excellent, which seems really strange. When Carmela touched these, she reported that this one felt colder than this one did, which actually makes sense. This is made of aluminum, okay? And because it's a metal with free electrons, even though these are the same room temperature, as soon as Carmela touched this, some of the heat was leaving her hand, going right into the block, and her brain was tricked into thinking it was actually colder, which is really funny. So you're probably thinking, okay, what's the other block made of? This is a plastic rigid foam. Now, plastic is not a great conductor of thermal energy, and plus there's little bubbles of air in there, which even resists heat transfer that much more. So we could have the ice cube here. It took a long time to melt, and we saw how quickly it melted over there. You did a great job investigating thermal conduction today, and I'm sure you will agree, this is a hot topic. So remember, my friends,
stay curious
and keep experimenting.
Get your Curiosity Guide and see more programs at WKAR.org.
Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. By the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources. More information is available at consumersenergy.com/foundation. Consumers Energy Foundation, supporting education and building sustainable communities in Michigan's hometowns. And by viewers like you. Thank you.
Let me think about this for a second. I need to come up with the perfect response.
The temperature for flash point for the... I'm gonna try that again. Isn't she good at that?
Yeah, Zoe!
Zoe. Patrice, those are the coolest shoes I've ever seen.
Thank you.
Remember, stay curious. Can I have them?